All right, there are two spaces that you're already familiar with in a mathematical context. R, which I could write if I wanted to as R1, or one space, one-dimensional space. We represent that geometrically as just a number line. Okay. And if I wanted to identify a point in that space, it would correspond to just a single number. Maybe this is the number 2. Okay. So to specify where I am on the number line, it just takes me one number to indicate that. Okay. R2, which we can also call 2 space, occasionally you'll see that written as R cross R. That corresponds to the Cartesian product, is what it's called, of R with itself. That's just the two-dimensional plane, where we've got an x-axis and a y-axis. A point in this space, I could give it a single name and call it P, but to indicate where I am, it's going to take an ordered pair. So in two-dimensional space, the location where I am is indicated by a pair of numbers. It takes two numbers to indicate a location if I'm in two-dimensional space. Okay. And you're all very familiar with that because you've worked with the real number line and you've worked with the plane quite often. In fact, if we graph f of x equals x squared, well, the domain of that is just the real number line, and the codomain is also the real numbers. That would just be the vertical axis because that would be our y values. If I draw the graph actually lives in 2 space. One thing that's interesting to note, though, is the graph would be this parabola. Okay. Now, a parabola is something that's one-dimensional. This is a one-dimensional object that lives in a two-dimensional space. If I were to look at just some portion of the parabola, I could measure the length of that curve, but it wouldn't have any area. Okay. So when something is one-dimensional, the appropriate geometric measurement is its length. When something is two-dimensional, and a disk like so, not just the circle, but the filled-in disk, okay, that would have area. When something is two-dimensional, the appropriate measurement of that thing would be area. Now, those of you who are taking or have taken linear algebra will get a very formal definition of dimension in that class. I'm going to rely on just a very informal definition. So when I'm talking about the dimension of a space, the dimension of the space matches the number of coordinates that a point in that space would have. In one space, we just have a single number. In 2 space, we have 2 numbers. We have an ordered pair to indicate where a point is. And when I'm talking about a region in one of those spaces and what the dimension of that is, it's one-dimensional if I would talk about length. It's two-dimensional if I would talk about area. It would be three-dimensional if I would talk about volume. Okay. So this section, 12.1, is all about 3 space, which we can write as R3. You can call that 3 space. And you'll occasionally see it written as the Cartesian product of R with itself 3 times. We're not going to use this notation a whole lot this semester. I just wanted you to know that it's out there. Okay. So this is going to be 3-dimensional space. So a point in 3 space is going to require 3 coordinates. So in 2 space, we have 2 mutually perpendicular axes, an x-axis and a y-axis. In 3 space, we're going to have 3 mutually perpendicular axes. So I've got a model right here. Okay? And here's the way it works. This axis that's coming out towards you, and it would extend back behind us as well. I've actually broken off the negative x-axis, so this model is broken, but you can't really see if I hold it this way. This is the x-axis. The positive direction is coming forward. Negative x values would be moving backwards. This axis that goes left and right, that's the y-axis. Left is the negative direction, and right is the positive direction. Okay. And then the vertical axis is the z-axis. And so we've got to decide which way is going to be positive and which way is going to be negative. Which do you think should be positive? Yes, up is going to be the positive direction and down is the negative direction. Now, some people might say, why do we do it that way? Because we sort of are used to having x as the horizontal and y as the vertical axis. So if we're adding a third one, why not make z be the one that's coming straight out towards us? And we could, and some systems do that. But that's not the standard mathematical orientation that we're going to use. Okay. And the reason for that is because eventually we're going to be taking a look at some functions. When we take a look at functions of two variables, the input is going to be a point on the xy plane, which would now be this horizontal plane right here. The output is the z value. So used to the output being vertical, that the output is attaching a height to a point in the domain. And so by having the z-axis be vertical, we can preserve that notion. So that's going to be our choice. Now, we're going to be doing some graphing in 3-space, which is a little bit difficult because now I need to fit this 3-dimensional space on this 2-dimensional whiteboard. And you'll be fitting 3-dimensional spaces onto 2-dimensional pieces of paper. Okay. So there are a couple of ways to do it. Okay. What I usually do, and this is just my personal preference, is I'm going to draw a pair of axes that are actually perpendicular. That would represent what you see when you look straight forward. So that's the z-axis, and this left-right one is the y-axis. So I usually will draw the y and z axes so that they actually look perpendicular. Now what that means is that the x-axis is coming straight out of the board like so. Now if I try to draw it, that's not very effective, because if I draw it where it actually would be, I'm no longer drawing on the whiteboard. So we've got to sort of skew things. So I'm going to draw the x-axis like so. Notice I'm using a dotted line back here because that's behind us. This is coming forward. Okay. So it does sort of look like this, but I need to recognize that when I'm putting 3-dimensional space onto a 2-dimensional surface, not everything that's a right angle looks like a right angle. Okay. So this is my x-axis here. Okay. Now, the y and z-axis meet at a right angle, and that's fine. That looks like a right angle. But I know that the positive x-axis and the positive y-axis also meet at a right angle. Okay. So that this angle right here, even though it looks like an obtuse angle, is actually a right angle. And usually the way we denote a right angle is by putting this little perpendicular sign right here. You'll notice that when they're actually perpendicular, this forms a right angle. When they're not actually perpendicular, I made this parallel to the y-axis and this parallel to the x-axis. So I'm using a parallelogram that is not a perfect rectangle to represent a right angle. Okay, excellent. Now, if I have a point in 3-space, again, I can give it a nickname. I can just call it P. But an arbitrary point would be an ordered triple of numbers, an x, a y, and a z value. Okay. And so I can refer to the point just by the nickname P. I can refer to it by the ordered triple, and it's perfectly acceptable to write them next to each other. That just says that's the nickname, that's the full name for this particular point. Okay. All right, excellent. So let's actually, I mentioned there are a couple of ways that I can represent things. This is my preference. I like to sort of have the y-axis and the z-axis actually looking perpendicular. The other option is something like this, where you would have the x-axis here, the y-axis here, and the z-axis here, so that none of them is actually looks perpendicular to any of the others. Okay, that's also perfectly acceptable. Okay, it is important that this is x and this is y. This is what we call a right-handed system. Okay, so that here, this is the positive x-axis. If I take my right hand and I take the fingers and point them in the direction of the positive x-axis, so they're pointing out towards you now, I'm going to curl those fingers towards the positive y-axis, which is over here. Okay. My thumb points in the direction of the positive z-axis. Okay. Now, if I reversed the roles of x and y, so I made this x and this y, if I take my right hand and point in the positive direction of this axis, my fingers don't curl backwards, so I'd have to turn my hand upside down to curve towards that positive direction, and now my thumb is pointing down. We don't want that. We want it so that if you're pointing in the direction of the positive x, curling towards the positive y, the thumb points in the direction of positive z. Okay. And I will expect that when you're drawing graphs in 3-space, you respect this orientation. So I don't care whether your y and z axis look perpendicular or not, either of these is acceptable. What I usually do is I start with this. I find it helpful to have two of the axes looking perpendicular. But every once in a while I encounter a shape that I'm just really struggling to draw. And if I'm really struggling to draw the shape, I sometimes find that switching to this framework makes that particular shape easier. So you can play around with it a little bit and see what your preference is. Okay, we've been going for a little while, so I'm going to stop this video. When we come back in the next video, we're going to plot a point. Very exciting. You're in 3rd semester calculus, and we're going to learn how to plot points. Okay. Actually, in chapter 12, we're spending a lot of time just getting comfortable working in this 3-dimensional space. We're used to living in a 3-dimensional world, but we're not used to doing math in 3 dimensions, and we're not used to drawing pictures in 3 dimensions. So it takes a little while to get comfortable with this new framework.